Let's plug in these values into the reaction quotient expression and see if we get 125. Now, my prediction is that we will not get a value of 125, and the reason why I'm saying that is because there's a different number of moles of gas on the left side and the right side of this equation, so it is likely that Q will not be equal to K, and there will be a net conversion either from left to right or right to left. Let's go ahead and do the math. Welcome to AP Chemistry Review and Practice. My name is Michael Farabaugh, and I'll be your guide on the side as you strive toward that 5 on the AP Chemistry exam. Each episode will include answers and explanations to practice problems, along with advice to help you avoid common mistakes. So, are you ready to review and practice for the AP Chemistry exam? I hope so, because this lesson starts right now. Welcome back to AP Chemistry Review and Practice. In this lesson, I'll give you the chance to review and practice topics 7.9 and 7.10. As you can see on this slide, these topics fall under Unit 7 in the AP Chemistry curriculum, Equilibrium. You can add your comments and questions below this video, and you can also email me with your comments and questions at apchemistryreviewandpractice@gmail.com. Check out the links in the video description area, which include the link to the packet that accompanies this video. Now let's move on to the review for topic 7.9, Introduction to Le Chatelier's Principle, and topic 7.10, Reaction Quotient and Le Chatelier's Principle. I have decided to combine these two topics together because their essential knowledge statements are very similar to each other. So these are the essential knowledge statements from the AP Chemistry course and exam description for these two topics. Le Chatelier's Principle can be used to predict the response of a system to stresses such as addition or removal of a chemical species, change in temperature, change in volume or pressure of a gas phase system, or dilution of a reaction system. Le Chatelier's principle can be used to predict the effect that a stress will have on experimentally measurable properties such as pH, temperature, and color of a solution. And for topic 7.10, a disturbance to a system at equilibrium causes Q to differ from K, thereby taking the system out of equilibrium. The system responds by bringing Q, the reaction quotient, back into agreement with K, the equilibrium constant, thereby establishing a new equilibrium state. Some stresses, such as changes in concentration, cause a change in Q only. A change in temperature also causes a change in the value of K, or the equilibrium constant. In either case, the concentrations or partial pressures of species redistribute to bring Q and K back into equality. Now let's move on to the practice for these two topics. This is question 1. In question 1, we are given a balanced chemical equation involving a reaction between substances D2 and X2 to produce substance DX. We are also given an equilibrium constant, Kc, for this reaction. Kc is equal to 64 at a temperature of 500 Kelvin. So question 1 says the following. An equimolar mixture of D2 and X2 is placed in a previously evacuated reaction vessel and allowed to reach equilibrium at 500 Kelvin according to the equation shown above. And when the system reaches equilibrium, the substances in the reaction vessel have the following concentrations. So what I will do before I take a look at part A of question 1 is I will write the expression for the reaction quotient Q for this reaction. So that would be products over reactants. And because this is a QC as opposed to a QP, this involves hard brackets representing concentration as opposed to that capital P symbol representing partial pressures. So it will be concentration of dx squared, because of that coefficient of 2 in the balanced equation, divided by the product of the concentration of d2 times the concentration of x2. Now, what I will do is to plug in the three values that are listed for the concentrations of the substances at equilibrium and verify that, in fact, Q equals K. So we can see that the concentration of dx at equilibrium is equal to 4.80 molar. So that number goes in the numerator of my Q expression. And then the substances D2 and X2 have concentrations of 0.600 molar. So those values will go into the denominator of my Q expression. Now, when I pick up my calculator and I take 4.80 squared divided by the product of 0.6 times 0.6, I'm hoping that I get a value of 64. And in fact, I do. So when I do that math, that verifies that the reaction quotient Q is equal to the equilibrium constant K, and therefore this represents the system at equilibrium. Now, with Le Chatelier's principle, there is often a change or a stress placed on a system already at equilibrium. So here comes that stress or that change in part A. So in part A, it says additional D2, which happens to be one of the reactants, is added to the reaction vessel until the concentration of D2 becomes equal to 1.40 molar. Now notice that I've now increased the value of the denominator in this expression, which means you can tell that Q will become less than K at this moment. So in part A, it says to calculate the value of Q at the moment that the additional D2 is added to the reaction vessel. So now when I pick up my calculator, it's going to be a different calculation. I will not get 64. I will get a number that is less than 64. So 4.80 squared divided by the product of 1.4 times 0.6, this gives me a numerical value of 27.4. So the answer to part A is 27.4, and then I will remind you that Q is less than K because 27.4 is less than 64. Now, in a previous episode of AP Chemistry Review and Practice, when I was discussing topic 7.7, calculating equilibrium concentrations, one of the essential knowledge statements says that when Q, the reaction quotient, is less than K, the equilibrium constant, the reaction will proceed with a net consumption of reactants and a generation of products. So take a look, I've drawn an arrow indicating that when Q is less than K for this situation in part A of this question, this leads to a net conversion from reactants to products or from left to right. So now let's move on to part B of this question, and we'll see what happens as equilibrium will be reestablished for this system. So here is part B. We are given a data table, and we can see that in the data table there are two question marks. So that is what we need to determine in part B. It says, when equilibrium is reestablished at 500 Kelvin, the concentration of dx, which is the product, in the reaction vessel, is equal to 5.26 molar, as shown in the table above. Note that 4.80 molar was the concentration of dx. Now it's 5.26, so that verifies that there was a net conversion from left to right, or from reactants to products, when equilibrium was reestablished. So what we need to do in part B is to calculate the concentrations of D2 and X2 in the reaction vessel when equilibrium is reestablished. And the strategy that I will use to answer part B is a strategy that I had mentioned in a previous episode of AP Chemistry Review and Practice, and that is to create a so-called RICE table, where the word RICE is an acronym for reaction, initial, change, and equilibrium. So for this system, at the moment when additional D2 is added to the reaction vessel, the concentration of D2 is 1.40 molar, the concentration of X2 is 0.600 molar, and the concentration of dx is 4.80 molar. Now, with respect to the change, there will be a net conversion from left to right, from reactants to products, but remember that the magnitude of the changes for the reactants and products in your rice table should be in proportion to the coefficients in the balanced chemical equation. So let's take a look at our coefficients. From left to right, that would be 1, 1, and 2. So I would expect that the change would be in terms of x, and 2x. So minus x, and 2x represents the magnitude of the changes with respect to this net conversion from left to right as the system reestablishes equilibrium. Now, at the moment, we do not know the concentration of D2 after equilibrium is reestablished. We also do not know at the moment the concentration of X2 when equilibrium is reestablished. But we do know that when equilibrium is reestablished, the concentration of dx is equal to 5.26 molar. And now that I have both the initial and the equilibrium concentration for dx, I can calculate the change. So what's the difference between 5.26 and 4.80? Well, that's a difference of 0.46. And if 0.46 is equal to 2x, then x would be half of that value. So what number is half of 0.46? Well, that would be 0.23. So in the change row of my rice table, I have minus 0.23, minus 0.23, and plus 0.46. All I have to do now to answer part B is do the math for substances D2 and X2. So what is 1.40 minus 0.23? Well, that would be 1.17 molar, which represents the concentration of D2 in the reaction vessel when equilibrium is reestablished. And then similarly, if I take 0.600 and I subtract 0.23, I get 0.370 molar, which represents the concentration of substance X2 in the reaction vessel when equilibrium is reestablished. So now we have officially answered part B. We have calculated the concentrations of substances D2 and X2 in the reaction vessel when equilibrium is reestablished. And now there's only one more part remaining, which is part C of question 1. Now in part C of question 1, this will be a verification. So based on the given information and your answers to part B, show the setup for the calculation of the reaction quotient Q that verifies that Q equals K when the equilibrium has been reestablished at the end of this experiment. So remember how the value of K is equal to 64. We are hoping that when we plug in these values into this reaction quotient, so there's my reaction quotient expression, and the values that I will be using for concentration come from the final row of my rice table. So that would be 5.26 molar in the numerator for the concentration of dx, 1.17 molar and 0.370 molar in the denominator for the concentrations of substances D2 and X2 respectively. Now when I pick up my calculator, I'm hoping to get that Q equals K, which equals 64. It's possible that I will get 63.9 or 64.1, but my value should be relatively close to 64, indicating that equilibrium has been reestablished. So when I pick up my calculator, 5.26 squared divided by the product of 1.17 times 0.37, in fact, I do get a number, 63.9, which is pretty close to 64. So therefore, I can say with confidence that this does verify that equilibrium has been reestablished in part C. So now that you've seen the answers to parts A, B, and C of question 1, it is time to move on to our next question. And this is a question set. So questions 2 through 4 in this packet refer to the following information. So we are given information that tells us the following. It says, the reaction system represented above is at equilibrium at 298 Kelvin. So in this balanced chemical equation, I see one reactant and two products. So the reactant is solid calcium carbonate, CaCO3, and one of the products is solid calcium oxide, CaO, and the other product is gaseous carbon dioxide, CO2. And we are also given the delta H, or the change in enthalpy for this reaction, and it's listed as 178 kilojoules per mole of reaction. Let's go ahead and take a look at the details for question 2. So in question 2, it says a student makes the claim that at the moment when a small amount of solid calcium carbonate is removed from the reaction vessel at constant temperature, the value of the reaction quotient Q will be greater than that of the equilibrium constant K for this reaction. So do you agree or disagree with the student's claim? Justify your answer. So what I will do is I will make an attempt at writing the equilibrium constant K for this reaction. So that would be products over reactants. So we have solid calcium oxide and gaseous carbon dioxide for the products, and we have solid calcium carbonate for the reactant. Now, what I have just written on this slide is followed with a set of question marks. So that indicates that it is possible that I have made a mistake, and yes, in fact, I have made a mistake. So I did this because this might be a mistake that some students would make when they write the equilibrium constant expression for a reaction that involves either solids or pure liquids. So this goes back to an earlier episode of AP Chemistry Review and Practice, and when I was talking about topic 7.3, reaction quotient and equilibrium constant, you can see at the bottom of this slide that one of the essential knowledge statements for topic 7.3 says the reaction quotient, or the equilibrium constant expression, does not include substances whose concentrations or partial pressures are independent of the amount, such as for solids and pure liquids. So because solid calcium carbonate should not be included in the equilibrium constant expression, as well as solid calcium oxide, the correct equilibrium constant expression, Kc, looks like the following. And now, based on that correction of that mistake that I had made earlier, just to show you that solids are not included in the equilibrium constant expression, then here is the answer to question 2, which is going to begin with the phrase, I disagree. So a student makes the claim that at the moment when a small amount of solid calcium carbonate is removed from the reaction vessel, the student claims that the value of Q will be greater than K. So I disagree. Solid calcium carbonate does not appear in the equilibrium constant expression. So as a result, decreasing the amount of solid calcium carbonate in the reaction mixture by removing a small amount will have no effect on the value of the reaction quotient Q for this reaction. So the message here is that adding or removing a small amount of a solid has no effect on the value of the reaction quotient Q. All right, well, hopefully that answer to question 2 makes sense. As we move on to question 3, we will still consider this same reaction system. So here is question 3, which is a multiple choice question. In question 3, it says the following. In a separate experiment, the volume of the reaction vessel is rapidly doubled with no change in temperature. Which of the following correctly predicts and explains how the number of moles of solid calcium oxide, which is one of the products, will be affected by this change? And we can see among the 4 answer choices the word increase or decrease with respect to the number of moles of solid calcium oxide, and then we can see the phrases less than K or greater than K with respect to the reaction quotient Q. So now what I'd like to show you on this next slide, this comes from my video for topics 7.6 to 7.10, and that is included in my YouTube playlist that's organized by AP Chemistry CED units. And so what it says on this slide is the following. Changes in the volume of the reaction vessel can cause a disturbance in a gaseous equilibrium system when there are different numbers of moles of gas on opposite sides of the chemical equation. Now, the consequences of these changes are summarized in the table below. Assume that the changes in the volume of the reaction vessel occur at constant temperature. So, how is the volume of the reaction vessel changed? Well, one possibility is that the volume of the reaction vessel is decreased. So if that were to happen, the partial pressures of all gaseous species increase, and the system shifts toward the side of the equation that has a lower number of moles of gaseous particles. Now, on the other hand, what's happening in this question is that the volume of the reaction vessel is increased. And so if that were to occur, the partial pressures of all gaseous species decrease, and the system shifts toward the side of the equation that has a higher number of moles of gaseous particles. And as you may know, there is an inverse relationship between gas pressure and gas volume, such that if I were to decrease the volume of the reaction vessel, then all of the partial pressures would increase. But on the other hand, if I increase the volume of the reaction vessel, then all of the partial pressures would decrease. So whether it is a Kc or a Kp, if the volume of the reaction vessel is rapidly doubled, then either the concentration or the partial pressure of that gas will suddenly be reduced. So double the volume, cut the partial pressure in half. Double the volume, cut the concentration in half. And so if the value of the concentration of CO2 is reduced to half its original value, then what happens to the reaction quotient? Well, the reaction quotient now becomes less than K for this particular situation. So what happens when Q becomes less than K? There will be a net conversion of reactants to products. So as you can see on the top of this slide, I'm showing an arrow to indicate a net conversion from left to right, or from reactants to products, when Q is less than K. So for this question, we are told that the volume of the reaction vessel is rapidly doubled with no change in temperature, and now we have to predict how will the number of moles of calcium oxide, which is a product, be affected. And then what about the Q versus K comparison? So you can hopefully see that the correct answer to question 3 is going to be choice C. The number of moles of calcium oxide will increase because there is a net conversion from reactants to products, or from left to right, and that's because under these conditions, Q becomes less than K. All right, well, hopefully that explanation for question 3 makes sense. We have another multiple choice question to consider in this set. So now let's go ahead and take a look at question 4. So question 4 says the following. In a separate experiment, the temperature of the system is decreased. Which of the following correctly predicts how the number of moles of solid calcium carbonate, which is the reactant, and how the value of the equilibrium constant K will be affected by this change? So something that's very important to remember is that if the temperature remains constant, then the value of the equilibrium constant K also remains constant. But on the other hand, if the temperature changes, then the value of the equilibrium constant K is going to change. And you can see among the 4 answer choices in question 4 that we have to determine if the value of the equilibrium constant K will decrease or increase. And then depending on the direction of the shift in the equilibrium position, will that cause the number of moles of solid calcium carbonate, which is a reactant, to decrease or increase. So like I had mentioned earlier in this lesson, there is a video on my AP Chemistry CED Units YouTube playlist that is for topics 7.6 to 7.10. And so what you're looking at on this slide is what I had mentioned in that video. And this is specific for changes in temperature. So this is what I had said in that video. If the temperature of an equilibrium system is increased, then the system will shift in the direction of the endothermic process. Now, that could be from left to right or from right to left, depending on whether the reaction is classified as endothermic or exothermic. Now, on the other hand, if the temperature of an equilibrium system is decreased, then the system will shift in the direction of the exothermic process. Again, that could be either from left to right or right to left, depending on if the reaction is classified as endothermic or exothermic. And as I had mentioned a few moments ago, changes in temperature cause the value of the equilibrium constant to change. Now, if the temperature change causes a shift toward the right, toward the products, then the value of the equilibrium constant K will increase. But on the other hand, if a temperature change causes a shift toward the left, toward the reactants, then the value of the equilibrium constant K will decrease. Now, also in that video, I had presented 4 different scenarios or possibilities. And the reason why there are 4 different possibilities is that the temperature of the system could either increase or decrease, and then the reaction could be classified as either endothermic or exothermic. So that results in 4 possibilities. I will consider each one of those possibilities right now. So suppose that the temperature of the system is increased, and suppose that the reaction is classified as endothermic. Well, there would be a shift in the endothermic direction, which would be from left to right toward the products, and the value of the equilibrium constant K would increase. Okay, here's another possibility. Suppose that the temperature of the system is increased, but the reaction is classified as an exothermic process. You will still have a shift in the endothermic direction, but that would be from right to left, so from products toward reactants, and that would cause the value of K to decrease. Okay, 2 more possibilities. Suppose that the temperature of the system is decreased and the reaction is classified as endothermic. Well, there would be a shift in the exothermic direction, which would be from right to left, from products to reactants, and this would cause the value of K to decrease. And then the last possibility, suppose that the temperature of the system is decreased and the reaction is classified as exothermic. There would be a shift in the exothermic direction, which would be from left to right, from reactants to products, and that would result in an increase in the value of the equilibrium constant K. Okay, now that you've seen all 4 of those possibilities, let's go back and revisit the details of question 4. Now, some of you watching this video might be wondering, how do we know, just by looking at a chemical equation, whether it's classified as endothermic or exothermic? Well, if you are given the change in enthalpy, or the delta H for the reaction, then you can focus on the sign of delta H. So in this problem, we can see that the sign of delta H is positive, and that means that the reaction is classified as endothermic. And then how was the temperature changed in this question? Well, the temperature of the system is decreased. Now let's consider that particular situation in which the temperature of the system is decreased and the reaction is classified as endothermic. So if the temperature of the system is decreased and the reaction is classified as endothermic, there will be a shift in the exothermic direction, which would be from right to left, from products to reactants, and the result is that the value of K would decrease. So now that we know what's going on here in question 4, we can choose the correct answer. So I'm showing an arrow indicating a net conversion from products to reactants, so from right to left. I'm indicating that the value of K will decrease. So the correct answer, based on the value of K decreasing, is either choice A or choice C. But considering that a shift from right to left will cause the number of moles of calcium carbonate to increase, that means that the correct answer to question 4 is choice C. The temperature of the system is decreased, The reaction is classified as endothermic. There will be a shift from right to left, and then that causes the value of K to decrease. And since calcium carbonate is a reactant, the number of moles of calcium carbonate will increase. All right, well, hopefully that explanation made sense. We have now completed the set of questions 2 through 4. So now let's move on to a different experimental situation. This is question 5. So here in question 5, we have a gaseous equilibrium system involving N2O4 and NO2, and then the change that occurs is a small amount of helium gas is added to the reaction vessel. So let's begin with what we know before the helium is added. It says a mixture of the gases NO2 and N2O4 is placed in a rigid, previously evacuated container, and when the system reaches equilibrium at 70 degrees Celsius, according to the equation shown above, the partial pressure of each gas is listed below. So we have a partial pressure for N2O4 of 1.33 atmospheres, and we have a partial pressure of NO2 of 2 atmospheres. Now, what I will do is I will write the expression for the reaction quotient Q, and this would be a QP as opposed to a QC, that is P for pressure as opposed to C for concentration. So instead of writing hard brackets to indicate the concentration of each substance, I've written the capital P to indicate the partial pressure of each substance. So it would be partial pressure of NO2 squared, because of that coefficient of 2 in the balanced equation, divided by the partial pressure of N2O4. So the partial pressure of NO2 is 2 atmospheres. The partial pressure of N2O4 is 1.33 atmospheres. And if I do 2 squared divided by 1.33, and I get a value of approximately 3, then this indicates that the value of the reaction quotient, Q, is equal to the value of the equilibrium constant, K, and this would be a system that is at equilibrium. Now let's go ahead and introduce a small amount of helium gas to the container. So here comes the change or the stress on the system. A small amount of helium gas is added to the container, increasing the total pressure of the gas mixture to 4 atmospheres. Assume that the temperature and the container volume remain constant, and at the moment when the sample of helium gas is added, here is the question that we need to consider. Does the value of the reaction quotient Q decrease, increase, or remain the same? Justify your answer. So now that we have added the helium, the total pressure is the sum of the partial pressure of the NO2 plus the partial pressure of the N2O4 plus the partial pressure of the helium. And the combined pressure of all 3 of those gases is 4 atmospheres. So what is the partial pressure of the NO2? It remains at 2 atmospheres. So that hasn't changed. What is the partial pressure of the N2O4? It also remains at the same value of 1.33 atmospheres. Now, helium was added, and the total pressure is 4 atmospheres. So 4 minus 2 minus 1.33, that gives us a partial pressure of 0.67 atmospheres. But the more important thing for us to consider is not the partial pressure of the helium, but take a look at these values. These partial pressures for NO2 and N2O4 have not changed. They are not affected when that small amount of helium gas is added to the container. And so if these partial pressure values have not changed, then the numerical value of the reaction quotient, Q, also has not changed. So what we're considering in this particle diagram is that we had a mixture of the gases NO2 and N2O4, as you can see in this particle diagram. Now, a small amount of helium gas is added, which are represented by the blue circles in this diagram, but the partial pressures of NO2 and N2O4 remain the same. Therefore, the value of the reaction quotient Q is still equal to 3.0. And the system remains at equilibrium after the helium is added because Q still is equal to K. So the official answer to question 5, hopefully this is all making sense to you, is the following. Does the value of the reaction quotient Q decrease, increase, or remain the same? The answer is that the value of the reaction quotient Q remains the same. The partial pressures of NO2 and N2O4 remain the same after helium is added. Okay, well, hopefully that answer and explanation makes sense for question 5. Now, let's go ahead and take a look at question 6. Here in question 6, we have another example of a gaseous equilibrium system, but this time, instead of adding a small amount of a gas such as helium, the change that will occur in question 6 will be a change in the volume of the reaction vessel. But we're not quite there yet. Let's go ahead and process what we know so far for this system involving the substances AQ2, Q2, and AQ3. So it says in question 6 that a mixture of AQ2 and Q2 is placed in a previously evacuated reaction vessel, and when the system reaches equilibrium at 400 Kelvin, according to the equation shown above, the partial pressure of each gas is listed below. So we have 0.4 atmospheres for the partial pressure of AQ2, we have 0.2 atmospheres for the partial pressure of Q2, and we have 2 atmospheres for the partial pressure of AQ3. So I will write the expression for the reaction quotient Q. Now that would be QP as opposed to QC, which is why I'm using partial pressures and not hard brackets to indicate concentration. And its products over reactants, you can see that I've got the exponent of 2 for the chemicals that involve a coefficient of 2. So partial pressure of AQ3 squared because of that coefficient of 2, and then divided by the partial pressure of substance AQ2, also squared because of its coefficient of 2, and then in the denominator is the partial pressure of Q2 as well. So now what I will do is plug in the appropriate partial pressures, and let's see if this system is in fact at equilibrium. So the 2 atmospheres will go in the numerator of this Q expression. The 0.4 atmospheres and the 0.2 atmospheres, those values will go in the denominator of this Q expression. Now I will pick up my calculator and let's see if we get 125. So 2 squared divided by 0.4 squared, and then also divided by 0.2, yes, we do get 125, which means that the reaction quotient Q is equal to the equilibrium constant K, and if Q equals K, then this represents the system at equilibrium. So now here comes the stress or the change to the system. So as we move on to part A of this question, this is the stress or the change. The volume of the reaction vessel is decreased from 2 liters to 1 liter, while the temperature is held constant at 400 Kelvin. So in part A, we have to calculate the partial pressure of each gas at the moment that the volume of the reaction vessel is decreased from 2 liters to 1 liter. So if you take a volume of a gas and you decrease the volume by cutting the volume in half, then the partial pressures will now be increased by a factor of 2. So because of that inverse relationship between pressure and volume, each partial pressure value has been doubled because the volume of the reaction vessel has decreased by half, or from 2 liter to 1 liter. So 0.4 atmospheres becomes 0.8 atmospheres, 0.2 atmospheres becomes 0.4 atmospheres, and 2 atmospheres becomes 4 atmospheres. Now, you might be wondering, without picking up your calculator, mathematically, are we still going to get a value of Q for the reaction quotient that is equal to 125 or not? Well, we don't need to guess. We will actually do this calculation right now. So the answer to part A is 0.8 atmospheres for AQ2, 0.4 atmospheres for Q2, and 4 atmospheres for AQ3. Let's move on to part B and start calculating the value of the reaction quotient. So based on your answer to part A, calculate the value of the reaction quotient Q at the moment that the volume of the reaction vessel is decreased from 2 liters to 1 liter. Let's plug in these values into the reaction quotient expression and see if we get 125. Now, my prediction is that we will not get a value of 125, and the reason why I'm saying that is because there's a different number of moles of gas on the left side and the right side of this equation, so it is likely that Q will not be equal to K, and there will be a net conversion either from left to right or right to left. Let's go ahead and do the math. So in the numerator of this expression, the pressure of AQ3 is 4 atmospheres. In the denominator of this expression, we have a partial pressure of AQ2 of 0.8 atmospheres and a partial pressure of Q2 of 0.4 atmospheres. I pick up my calculator and it's going to be 4 squared divided by 0.8 squared and then also divided by 0.4. Aha! We do not get 125, which means Q is not equal to K, so there will be a net conversion. Now that's either from left to right or right to left, but clearly we can see that the answer to part B is not 125. So the system is no longer at equilibrium for the moment. So the answer to part B is Q is equal to 62.5. And since 62.5 is less than 125, which is the value of the equilibrium constant K, then we can say that Q is less than K for the moment. And remember that when Q is less than K, there will be a net conversion from reactants to products. So you can see on this slide, I'm showing an arrow indicating that when Q is less than K, there will be a net conversion from reactants to products or from left to right. Now let's move on to part C of question 6. In part C, it says that when equilibrium is reestablished at 400 Kelvin, the partial pressure of substance AQ3 in the reaction vessel is not 4 atmospheres, it's actually 4.15 atmospheres. So that would be verification that there was additional product formed and there was a net conversion from reactants to products or from left to right. So just like we saw earlier in this lesson, to calculate the partial pressures of the other 2 gases in the reaction vessel, this would be a good strategy to create a so-called rice table. So here is our rice table. So before the system has reestablished equilibrium, we had initially 0.8 atmospheres for AQ2. We had 0.4 atmospheres for Q2, and we had 4 atmospheres for AQ3. And now where should we put that value of 4.15 atmospheres? So I will place the value of 4.15 atmospheres in the bottom row of the rice table. Now, what about the change row of the rice table? Remember that the magnitude of the changes for the reactants and products in your rice table should be proportional to the coefficients in the balanced chemical equation. And so from left to right, these coefficients are 2, 1, and 2. And so in terms of x, that would be 2x, x, and 2x. And because there is a net conversion from left to right in this scenario as the system reestablishes equilibrium, then that will be minus 2x for the reactant, AQ2. It would be minus x for the other reactant, Q2. And then it would be plus 2x for the product, AQ3. Now I will place that value of 4.15 atmospheres in the bottom row of this rice table. So that is the partial pressure of the AQ3 when equilibrium has been reestablished. So what's the difference between 4.150 and 4? Well, that's a difference of 0.15. And if 0.15 is equal to 2x, that means that x would equal half of that value. So what's half of 0.15? Well, that would be 0.075. So the change row of my rice table looks like this: minus 0.15, minus 0.075, and plus 0.15. Now to calculate the partial pressures of AQ2 and Q2 in the reaction vessel when equilibrium is reestablished, what is 0.8 minus 0.15? Well, that would be 0.65 atmospheres. So that's the partial pressure of AQ2 in the reaction vessel when equilibrium is reestablished. And what is 0.4 minus 0.075? Well, that would be 0.325 atmospheres. That's the partial pressure of substance Q2 in the reaction vessel when equilibrium is reestablished. So we have now answered part C of question 6. We have calculated the partial pressures of AQ2 and Q2 in the reaction vessel when equilibrium is reestablished. And so now I would like to do that verification step for part D. So what do I mean when I say verification? Well, let's go ahead and verify that Q equals K. So based on the given information and your answers to part C, show the setup for the calculation of the reaction quotient Q that verifies that Q equals K when equilibrium has been reestablished at the end of this experiment. So in the numerator will be 4.150. That's the partial pressure of AQ3 at equilibrium. And in the denominator, it will be those values that we calculated in part C, which are 0.650 for AQ2 and 0.325 for Q2. Now, when I pick up my calculator, I'm really hoping that I get Q equals K equals 125. So here we go, 4.15 squared divided by 0.65 squared, and then divided by 0.325. Did I get 125 when I did that math? Yes. So this does verify in part D of question 6 that equilibrium has been reestablished. All right, well, hopefully all of those answers and explanations made sense. We are now ready to move on to our next question. So this is question 7. Now, if you read the details of the experiment described here in question 7, you will notice that a temperature change occurred. And if you remember what I had mentioned earlier in this lesson regarding those 4 different situations, temperature increased, temperature decreased, is the reaction classified as endothermic or exothermic, then knowing which one of those 4 different situations occurred for question 7, that will help you answer this question. So let's go ahead and take a look at the details of question 7, which involves a temperature change. In question 7, it says that hydrogen gas and iodine gas react to form hydrogen iodide as represented by the following equation. So not only do we see a balanced chemical equation, but we can see that the delta H, or the change in enthalpy for this reaction, is negative 12.2 kilojoules per mole of reaction. And it goes on to say that samples of hydrogen gas and iodine gas are added to a previously evacuated reaction vessel and allowed to react. And a chemist monitors the number of moles of hydrogen iodide gas over time. And you can see that on the y-axis in this diagram, it says moles of hydrogen iodide gas. And on the x-axis in this diagram, that would be time. And of course, there's also a label, a dashed line. It says at time t, the temperature of the system is changed. Now, we don't know whether the temperature was decreased or increased. That is what we need to answer in question 7. It just says that at time t, the temperature of the system is changed. As a result of the temperature change, the number of moles of hydrogen iodide gas in the reaction vessel is affected. And you will notice that to the right of that dashed line, you can see that the number of moles of HI, or hydrogen iodide, has now been increased a little bit. All right, well, the chemist did not add more hydrogen. The chemist did not add more iodine or add more hydrogen iodide to the system at time t. The only change that we need to worry about is a change in temperature. So here are the details of the experiment in question 7. At this point, at time t, the temperature of the system is changed. At this point, from that increase in the number of moles of hydrogen iodide, which is a product, then after time t, we can see that there was a net conversion from reactants to products because additional product, HI, was produced. So I'm showing an arrow indicating that there was a net conversion from reactants to products as a result of the temperature change. And what about that sign of delta H? Now, earlier, we saw that the sign of delta H was positive and the reaction was classified as endothermic, but here in question 7, we can see that the opposite is true. The sign of delta H is negative, and so that means that this reaction is classified as exothermic. Remember those 4 scenarios or situations that I had presented earlier in this lesson? That is our job right now. We have to consider what sort of temperature change would cause this exothermic reaction to experience a net conversion from left to right. So this is the scenario. Was the temperature increased or decreased? Well, to get an exothermic reaction to experience a net conversion from left to right, this is what has to occur. The temperature of the system is decreased. An exothermic reaction would result in a shift in the exothermic direction, so from left to right. So now we can answer question 7. The reaction is exothermic. It experienced a net conversion from left to right, so we can say that the temperature of the system is decreased. So here is our answer to question 7. So just as a quick reminder, it says, at time t, did the temperature of the system decrease or increase? Justify your answer in terms of the information in the diagram above and in terms of the change in enthalpy for the reaction, delta H. So this is what I said for question 7. After time t, the diagram shows an increase in the amount of hydrogen iodide, which is a product formed in this reaction. The forward reaction, so from left to right, is exothermic because the sign of delta H is negative. And if the temperature of an equilibrium system is decreased, then the system will shift in the direction of the exothermic process, which in this case is from left to right. So my answer is, at time t, the temperature of the system decreased, resulting in a net conversion from left to right. All right, well, hopefully that situation regarding a change in temperature and the effect on an equilibrium system, hopefully all that makes sense to you. We have 2 more questions in this packet. Let's move on to question 8. In question 8, it says, a chemical system at equilibrium is represented above. So we can see a balanced chemical equation, and we can see that the change in enthalpy, or the delta H, is positive 13 kilojoules per mole of reaction. It says for each of the following stresses listed in the table below, we have to circle the correct choices based on Le Chatelier's principle. So what we have to do is consider how will the number of moles of HOCl be affected, and HOCl happens to be a product of this reaction, and then how will the value of the equilibrium constant K be affected. So our first stress is adding a catalyst at constant temperature. Now, when I see constant temperature, that gives me a clue about whether the value of K will be affected or not. So if the temperature remains constant, then the value of K also remains constant. So I will go ahead and circle remains the same for the value of K. Now, what does a catalyst do? Well, a catalyst will typically provide a lower activation energy pathway, and that will speed up a reaction. But this is a reversible reaction. So what a catalyst will do is not only speed up the reaction rate for the forward reaction, the catalyst will also speed up the reaction rate for the reverse reaction as well. So the system should reach equilibrium at a faster rate. However, a catalyst should not affect the value of K. The catalyst should not affect the relative amounts of the reactants and the products that are present at equilibrium, so we do not expect a net conversion from left to right. We do not expect a net conversion from right to left. We simply would reach equilibrium at a faster rate. So the answer for this first part is that there would be no shift in the equilibrium position, so the number of moles of HOCl will not be affected. So that would remain the same for both the number of moles of HOCl and the value of the equilibrium constant K. Let's go ahead and take a look at our next stress. Now, this stress also involves constant temperature, so I'll focus on that first. Again, if the temperature remains constant, the value of K also remains constant, so I will circle remain the same for K. But we are removing a small amount of Cl2O, which happens to be a reactant. So I'm going to write the expression for the reaction quotient Q, so that's concentration of HOCl squared divided by the product of the concentration of Cl2O times the concentration of H2O. Those are my two reactants. You'll notice that Cl2O is not only a reactant, but it appears in the denominator of this reaction quotient expression. So mathematically, if we remove a small amount of Cl2O and that concentration decreases, it creates a situation in which the reaction quotient Q becomes greater than K. So what happens if Q becomes greater than K? If Q is greater than K, then there should be a net conversion from products to reactants, or from right to left. So you can see I have drawn an arrow indicating that when Q becomes greater than K, there is a net conversion from right to left, and so that would mean that the number of moles of HOCl would decrease. So removing a small amount of one of the gaseous reactants will cause Q to become greater than K. The number of moles of HOCl will decrease as the system tries to reestablish equilibrium, but the value of K remains the same because the temperature remains constant. Let's go ahead and consider our next stress. So our next stress is, what if we decrease the volume of the reaction vessel at constant temperature? Again, there's that constant temperature, so the value of K remains constant. Now, what happens when the volume of the reaction vessel decreases? Well, changes in the volume of the reaction vessel can cause a disturbance in a gaseous equilibrium system. But that's only when there are different numbers of moles of gas on opposite sides of the chemical equation. Now, if we have 1 mole on one side and 2 moles on the other, then there would be a shift. Or if we have 2 moles on one side and 3 moles on the other, there would be a shift. But take a look at this balanced equation. I see 2 moles of gas on the left, and I see 2 moles of gas on the right, so there will not be a shift for this particular chemical equation. So what I'm saying is the following. The number of moles of gas in the numerator and denominator of the Q, or the K, are equal. So mathematically, if we decrease the volume of the reaction vessel, it will have the same effect on both the numerator and the denominator because we have the same number of moles of gas in the numerator and denominator. So decreasing the volume of the reaction vessel does not change the value of Q. And since Q remains equal to K, there will not be a shift in the equilibrium position. So the number of moles of HOCl will not be affected. So my answer is remain the same for both of these. Again, had there been a different number of moles of gas on the left compared to the right, then there would have been a shift. But if you have the same number of moles of gas on each side of the equation, then changing the volume of the reaction vessel will have no effect on the value of Q, and there will not be a shift in the equilibrium position. Now, so far we have seen constant temperature 3 times. Let's take a look at the last stress in question 8. Aha, now we do have a change in temperature. So what do we know? Increasing the temperature of the system, and we have to consider whether there will be a shift from left to right or right to left. But we can say with confidence that the value of K is going to change. So if the temperature changes, the value of K will change. Since the sign of delta H for this reaction is positive, that means that this reaction is classified as endothermic. And now that we know that the temperature is increasing and that this is an endothermic reaction, remember those 4 different scenarios that I had mentioned earlier in this lesson? Let's see which one of these scenarios will be applicable. So we have an increase in temperature for an endothermic reaction. Let's take a look. Endothermic reaction, increase in temperature. There will be a shift in the endothermic direction, so that will be from left to right. So now we can answer the last part of question 8. Endothermic reaction, a net conversion from left to right. So you can see I'm drawing an arrow from left to right, and K increases. So the value of K increases. If the temperature of an equilibrium system is increased, the system will shift in the endothermic direction, and so for this system, that will be from left to right, and the value of K will increase. So there's my arrow to indicate a net conversion from left to right. The number of moles of HOCl will increase as we experience a conversion from reactants to products, or from left to right, and the value of K will increase. All right, well, those are the answers and explanations for all parts of question 8. Now we have come to the last question in this packet. This is question 9, which happens to be a multiple choice question. In question 9, it says, for which of the equilibrium systems represented below will the amount of products at equilibrium increase if the volume of the reaction vessel is increased at constant temperature? So remember that changes in the volume of the reaction vessel can cause a disturbance in a gaseous equilibrium system, but that's only when there are different numbers of moles of gas on opposite sides of the chemical equation. So the first thing that I will do is see if I can eliminate any of the answer choices in question 9. So do we see any balanced chemical equations in question 9 where we have the exact same number of moles of gaseous reactants and products? So if you look closely, you can see that we can eliminate choice B. So in choice B, I see 2 moles of gas on the left, and I see 2 moles of gas on the right, so that reaction would not experience a shift in the equilibrium position if the volume of the reaction vessel is changed. Let's go ahead and eliminate choice B. Now what I will do is go back to choices A, C, and D and simply count the total number of moles of gas on the left side and the right side. So starting with choice A, I see 2 moles of gaseous reactants, and I see 3 moles of gaseous products. And then moving on to choice C, I see 2 moles of gaseous reactants, and I see 1 mole of gaseous products. And then finally in choice D, I see 4 moles of gaseous reactants, and I see 2 moles of gaseous products. Now I will consider the specific details. We need to get a shift from left to right in order to increase the amount of product, and then we also are increasing the volume of the reaction vessel. So which equilibrium system should experience a net conversion from left to right toward the products when the volume of the reaction vessel is increased? So if the volume of the reaction vessel is increased, the partial pressures, or the concentrations of all gaseous species, will decrease. And how will the system reestablish equilibrium? By experiencing a shift toward the side of the equation that has a higher number of moles of gaseous particles. So what I'm looking for is a balanced chemical equation where there is a greater number of moles of gaseous products as compared to reactants. So that's why the correct answer for question 9 is choice A, because if we increase the volume of the reaction vessel and there will be a shift toward the side of the equation that has more moles of gaseous products, then that will be from left to right in choice A. So increasing the amount of products at equilibrium. All right, well, hopefully that answer to question 9 makes sense, and we have now come to the part of the lesson where I give you advice to help you avoid common mistakes. So the first thing that I would like to mention is that if you need more practice problems related to Le Chatelier's principle, then you can review the information in my video for topics 7.6 to 7.10 and that video is linked in the video description area. Now, near the end of that video, you will see a summary of the following: how changes in temperature affect an equilibrium system and the value of K. I will give examples of various changes that can occur in an equilibrium system. I'll talk about the comparison of Q versus K that is directly related to each change and how the equilibrium system responds to each change. So on the next couple of slides here, this is an example of what that video includes with respect to a summary of Le Chatelier's principle. So I talk about a catalyst, I talk about solids and liquids, I talk about removing or adding a substance, I mention what happens if there is a dilution of an aqueous system with water, what happens in a gaseous equilibrium system if the volume of the reaction vessel is changed, adding an inert gas such as helium to a gaseous equilibrium system. I mention those changes in temperature and how K will be affected. So all of that is in that video from my YouTube playlist that's organized by CED units. Again, that would be topics 7.6 to 7.10, that video. Now, my next piece of advice is what I normally say in this point in the lesson. Read the question carefully and make sure you are answering the question that is being asked. Always show your work for your calculations, and specifically when you are answering a free response question involving Le Chatelier's principle, it is a really good idea to include a comparison of Q versus K if it is relevant to the experimental situation. So note, you cannot make a Q versus K comparison for changes in temperature, but what you can do is memorize those 4 different scenarios that I had mentioned in this lesson. So increasing or decreasing the temperature, and whether the reaction is endothermic or exothermic, be familiar with all 4 of those scenarios. Remember that if the temperature changes, the value of the equilibrium constant K will change. However, if the temperature remains constant, then the value of K also remains constant. And after you make the comparison of Q versus K, you can make one of the following conclusions regarding the shift in the equilibrium position. So you can say, since Q is less than K, then there will be a net conversion from reactants to products, or from left to right. Or you can say, since Q is greater than K, there will be a net conversion from products to reactants, or from right to left. But you have to be very specific. So if you use the phrase, according to Le Chatelier's principle, that is not a sufficient explanation. It is better to include a specific and correct comparison of Q versus K to support your claim on the AP Chemistry exam. And remember to avoid vague, unclear language, such as the following. If you say, it will increase, well, which substance are you referring to? So try to avoid using the word it in your responses. If you say, the concentration of the reactant will change, well, do you mean increase or decrease? How will it change? If you say that Q will become different than K, do you mean Q will become less than K or greater than K? So again, be specific and avoid vague, unclear language. All right, well, now we have come to the end of this lesson. In my next lesson, I'll give you the chance to review and practice the last 2 topics in Unit 7, which are topics 7.11 and 7.12. If you enjoyed this lesson, I invite you to like this video and subscribe to my YouTube channel. Check out the links in the video description area, which include the link to my YouTube playlist organized by AP Chemistry CED units. You can add your comments and questions below this video, and you can also email me with your comments and questions at APChemistryReviewAndPractice@gmail.com. Thank you for letting me be your guide on the side as you strive toward that 5 on the AP Chemistry exam. Keep studying, and I'll see you next time on AP Chemistry Review and Practice.